In this video, we will use inverse trig ratios as well as sine, cosine, and tangent in the Pythagorean theorem to solve right triangles. Recall, solve right triangles means to find all the missing parts in this right triangle. To make sure that I've actually solved the right triangle, I like to, for all of these problems, I like to draw myself a table that organizes the angles that are in the triangle as well as the side lengths. I'm going to label the side lengths in the following way. I'm going to label them using lowercase letters, and I'm going to label them, and those lowercase letters are going to be the angle they're opposite from. So for instance, here's angle x. So the side that's opposite of angle x will be side little x. Here's y. The side that's across from y will be little y. That's this one. And the side that's opposite of z will be little z. This is a common convention. We're going to be using it quite a bit in future lessons here. So to organize myself, I'm going to make a table. I'm going to look for, I need to know angle x, angle y, and angle z. I need to know side x, side y, and side z. And I'm going to start by filling in all the things I know. And I actually know three of these six things. I know that angle z is 90 degrees. I know that angle x is 52. And I know that side y is 8.5. Some things I can fill in right away. An easy one to fill in is this missing angle. Since I know the angles of a triangle add to 180, I could just do 180 minus 90 minus 52, which makes angle y 38 degrees. Maybe I'll fill that in over here as well. Knowing that, I can try to use sine, cosine, tangent, or the Pythagorean theorem, or whatever other method you so choose, to try to find the missing sides. So how about I'll try to find side x. I know if I use sine, cosine, and tangent, SOHCAHTOA, I know from angle x's perspective, I'm looking for side x, and I know side y. From angle x's perspective, that's the opposite side and the adjacent side. So opposite and adjacent, that's the trig function that uses that is TOA, or tangent. So I think the tangent of angle x, which is 52 degrees, is equal to the opposite side, which is x, over the adjacent side, which is 8.5. I could cross multiply this to get x times 1 is equal to 8.5 times the tangent of 52 degrees. And I use my calculator to figure out what this value is to the nearest tenth. That would be 8.5 times tangent of 52 degrees. And since I'm in degree mode, I don't need to type the degree symbol. If you're not in degree mode, you definitely want to add the degree symbol, which is in the pi button here. Hit enter, and that means that x is about 10.8795, or to the nearest tenth, about 10.9. So I'll fill in x is 10.9. From here, there are a lot of ways you could solve. There's multiple ways you could find side z. You could use a different trig function. You could use, like, say, how about cosine of 52 as adjacent and hypotenuse. You could use Pythagorean theorem because it's a right triangle, so you could say a squared plus b squared equals c squared. Whatever makes the most sense to you, go ahead and do it. I'm going to choose to use a trig function to get more practice with it. But again, you could use Pythagorean theorem and you'll get the same answer. And you can see other approaches in the filled-in version of these notes on Canvas. But from angle x's perspective, from this 52 degrees, I know the adjacent side is 8.5, and I'm looking for the hypotenuse. Adjacent hypotenuse is the ka of SOHCAHTOA. So that means the cosine of 52 degrees is equal to adjacent leg over hypotenuse. if I put a 1 underneath this, I could cross multiply and get z times the cosine of 52 degrees is equal to 8.5. To get z by itself, I divide it by this decimal of whatever cosine of 52 degrees is. And you get z is 8.5 divided by cosine 52, 8.5 divided by the trig cosine of 52, which is about 13.8. So z is 13.8. I've got measurements for all 6 parts of this right triangle. My triangle is solved. Let's try this again. Here's a description of a triangle. Solve a right triangle that has hypotenuse 9 and a leg that is 3. If there's not a picture, we're going to draw one. And this is a pretty bad right triangle, but it's a right triangle nonetheless. I'm going to label the corners just so that I have a better, so that I can speak more intelligently about what these things are, and I can label the parts. I know the hypotenuse is 9. That means this side is 9. One of these legs is 3. Well, we call this bottom one. Doesn't really matter. So using the kind of the same notation as before, the sides that are across from an angle, angles are in capital letters, and the sides will be lowercase letters. So I think this will be side A, this will be side B, and then across from angle C will be side C. And when I'll make a quick table here. In my triangle here, angle A, I need to find angle B and find angle C. I need to find side A, I need to find side B, and I need to find side C. I know 3 of these things. I know that angle B is 90 degrees. I know that side B is 9. And I know that side A is 3. I need to find these 2 missing angles in this missing side. Since I know 2 of the 3 sides, I could use Pythagorean theorem to find side C. That would be one approach I could take. In any event, I'm going to need to find these missing angles here. So I'm also going to probably have to use some, looking for angles, I'm going to have to use those inverse trig functions from our previous video. I mean, it doesn't matter where you start. Maybe I'll start with, since I noticed Pythagorean theorem first, I'll use that. I know that leg squared plus leg squared equals hypotenuse squared. So I know that 3 squared plus c squared is equal to 9 squared. Or 9 plus c squared equals 81. C squared is 72. So c is the square root of 72. Which is, in exact form, that's 6 roots of 2, which is to the nearest tenth as before. That's about 8.5. I can show that on my calculator. Square root of 72. So the nearest tenth, 8.5. So side C is about 8.5. Let's find these missing angles. I'm going to set up a, I'm going to, from angle A's perspective, use sine, cosine, or tangent to write a trig function. So from angle A's perspective, I know the opposite side and the hypotenuse. Sine uses opposite and hypotenuse. So I think the sine of angle A is equal to 3 opposite over hypotenuse, 3 over 9. And as we saw in the previous video, I want to find out what angle A is. I'm going to undo the sine with its inverse function. So I'll do the inverse of both sides, which tells me that angle A is the inverse sine of 3 over 9. So again, I can do, on my calculator, I'll do trig inverse sine of 3 over over 9, which works out to be about 19.4712, or to the nearest tenths place, how about 19.5? So angle A works out to be about 19.5 degrees. You could use subtraction. I'm going to use cosine. I'm going to use a trig function to find c just for practice, but you could just subtract here. But I would like to show you that it works out to be the same thing. From angle C's perspective, I know the adjacent side and the hypotenuse. So from angle C's perspective, the cosine of angle C is the adjacent over the hypotenuse. So that means that angle C is the inverse cosine of 3 over 9. And I'll finish this with the Google calculator just to show, that we can make sure we remember how to use it. I pull up a calculator on Google. I use the inverse cosine and make sure our degree is what's highlighted. To do the inverse cosine, I'm going to hit inverse and then cosine to bring up the inverse cosine button. It's written as arc cosine, is the other notation. 3 divided by 9. Hit enter. And the inverse cosine of 3/9 happens to be about 70.5 degrees. And what do you know? If I add 19.5, 90, and 70.5 together, we get 180, which is really nice. That's what it's supposed to be. So, in summary, here's the missing parts of this triangle. This is the triangle completely solved.